Hello everyone, and welcome back, Superstars. Today you're with Zach, and I'll be going over AP Chemistry topics 1.5 and 1.6, Photoelectron spectra, and electron configuration, briefly. So, first of all, regarding photoelectron spectra, this is a process that we can use in determination of relative energy of an electron, in terms of like an atom or ion. So how it works is it's based off the premise where radiation in the form of light or like photons can remove an electron from wherever it is. And what can we connect removing an electron to the last topic that we went over in one of my videos that has to do with periodic trends, which you should definitely go watch if you don't know. So pause for a second if you want to think about it, but for the sake of time, we're just going to go straight into it. PS measures the ionization energy of an electron, which is similar to what I said here, the relative energy of an electron. So a PS diagram would look like this, where the horizontal axis represents the energy, the relative energy or ionization energy of an electron, and it's decreasing, which I'll explain in a minute. And this vertical axis represents amount of electrons. So, as I said, peaks represent a relative amount of electrons. So, let's say, based off your reference here, where these peaks are equal to 2 electrons, what would this peak, which is I'll say is peak 3, how many electrons would this peak have? Pause for a second and think about it. But when you think of relativity and just that type of concept, since this is 3 times bigger, you can assume that this has 6 electrons, right? So let's think about it. 2 electrons, 6 electrons. What does this remind us of? A concept you probably learned in honors or normal chemistry that you took, which you're probably taking, or which you probably learned if you already if you're taking AP Chem right now or trying to learn it. So it's electron configuration. So, as I just previously mentioned, this kinda resembles the 1s2, 2s2, 2p6, and we can back this up by looking at this horizontal axis with decreasing relative energies. So if this is your 1s2 subshell, it would make sense because it has the highest relative ionization energy in comparison to this one, because of the properties of distance and how they affect ionization energy, which I also went over in the past video on periodic trends, which you should definitely check out for more context. And I kind of gave it away here, but you should be able to deduct that this PS diagram represents neon because of this electron configuration. And College Board is going to ask a lot of these questions, especially multiple choice, like what element or atom or ion does this PS diagram resemble? And you just need to pay attention to the amount of electrons present in the diagram, and you can basically make an electron configuration with that and then link it to the possible answers. So in terms of application, I drew 2 PS diagrams here, so I want you to think about what elements are being shown in diagrams 1 and 2. What are the respective electron configurations of 1 and 2? And I also want you to explain, in terms of atomic structure, why the ionization energy or relative energy of the respective valence electrons are different. So why is this shell over here closer to 1 than this valence shell over here, which you can see is closer to 10? So take a minute to think about that and pause the video and write it down, and I'll go over it in a second. Okay, so with what elements are being shown, we first of all see that right here you have 4 total electrons. So let's write out this electron configuration. We have our 1s subshell here, filled with both electrons, and our 2s as well. So that obviously codes for pause the video and think about it. I'll get back to that when we get to this one, because I want to do both of them at the same time. Okay, so right here we have 1s2, 2s2, and then this peak is relatively higher than this one, so let's say 2p6, because it's full. According to Aufbau principle, it would have to be full to continue on to this one. And let's say this is 3s2. So now pause the video, and I want you to think about what elements these electron configurations represent. Okay, so now that you guys hopefully have found an answer, we're going to say that since this has 4 electrons, this represents a beryllium atom. And since this has 12, we're going to say it represents magnesium. Both group 2 metals, so similar properties. And we kind of already did questions 1 and 2. So now question 3. This one's kind of more application to past chapters, which is likely to be how an exam question about PES would be formatted, especially if it's present in the FRQ. So explain in terms of atomic structure and periodic trends, I guess, why the ionization energy of the respective valence electron shells, which are the ones I circled here, are different. So pause the video and think, but I'm going to explain it right now. What's basically happening here is beryllium's atomic radius is smaller in comparison to magnesium's, therefore the distance between the nucleus and the valence shells are smaller here than here. And according to Coulomb's law, the model we looked at in the last video, distance is inversely proportional to the force exerted on a molecule, which we go over very in depth in that video. I just really want you to watch it because you'll understand this chapter and future chapters a lot more. So what that's basically saying is since beryllium has a smaller distance in between the particles, the force being exerted is greater, therefore it would take more energy to remove an electron, meaning it has a higher ionization energy, or the valence electron has a higher ionization energy in comparison to the valence electrons of magnesium. Okay, so I previously mentioned Aufbau's principle, where I never really explained that, but this part of the video is kind of going to be a little review on electron configurations from Honors Chem or Normal Chem, and I'll give you a little life hack of what you could do to never miss an electron configuration question ever. So Aufbau principle basically denotes that electrons must occupy the lower energy levels, or like build up from lower energy levels to fill higher ones. And the order of energy levels, it's determined by the PES, like which ones are before in the diagram. So valence electrons and reading electron configurations, this is also just a review. So tricks that I use to recognize elements fast is look at the end, and this represents the period, and you should know your blocks, your S, P, D, and F blocks. So since this is an S1, that means I know it's the group 1 first thing. It's the first thing in period 3, so I can immediately denote that that's Na. So you basically have to pay attention to these valence electrons, and yeah, the coefficient tells us the period. So applications of Aufbau principle. One really important thing that you're going to need to know about transition metals is your 4s subshell is going to fill in before your 3d subshell. So if scandium with this electron configuration ionizes into this form, what's the new electron configuration? I'll give you a minute to think about it, but just really quickly you could see that right here, scandium is losing 3 electrons. So basically imagine we X out these 3 electrons, so your new configuration is just equal to argon. And this is the most stable ion of scandium because now its valence shell is completely gone. But now what about Sc+, meaning that it only lost 1 electron? As we previously mentioned, we have our configuration as argon, Fs2, 3d1. So what would be the new electron configuration if it ionizes into this form. So basically what happens according to Aufbau principle is instead of losing its 3D shell, what it's going to do is first lose a 4s electron because it's at a higher energy level once filled. So the final answer for this will be argon 4s1 3d1. And I know that looks kind of sketchy, but that would be the right answer in this situation. So now, let's say the electron configuration of element X is this, which I hope by now you can identify immediately. And say X forms a chloride. What would the molecule, how would the molecule look like in terms of this? Okay, so let's think. We could look at the end or the valence shell of our electron configuration right here, and we see that we see 3 and 2 in the coefficient and superscript. So I will go to period 3 and look at the second group where I find magnesium, or the second group, and I find magnesium. So we're looking at magnesium right now. So second group elements have a charge of 2+. Therefore, if I were to form a chloride with this, it would be or XCl2. And now, say X wants to form a phosphate, so as we previously established, X has a 2+ charge, and we know phosphate has a 3- charge, hopefully by now. So what we're going to do is use the cross multiplication method and have our final answer as this. Sorry. So now with a scope of a few different types of questions, I hope that you're more familiar with Aufbau's principle, its applications, electron configuration, some of its applications alongside PES and how they all connect, especially with topics like atomic structure and periodic trends. But now onto the life hack, which I'm unable to show on the computer because I can't find any sufficient TI-84 websites that have this app downloaded. But, okay, say you're in the scenario where you're taking the AP exam tomorrow. I'm assuming that in your school you have access to graphing calculators like a TI-84. So what I want you to do is whenever you're free in your math class, grab a TI-84, go to the apps, tap the apps button, and I think it is either you tap 0 to access the periodic table, which is an app downloaded on a lot of school-administered TI-84s. And the things with this periodic table is you could see all the elements and all their atomic numbers and mass, but a sweet little trick that you can use is if you click on like a space on the periodic table, it takes you to like a new menu of just that element, and it tells you everything about it, like the mass, atomic number, and especially the important thing is it tells you the electron configuration and noble gas configuration. So say you're taking the AP exam tomorrow, you could just ask your math teacher, hey, can I grab a TI-84 to take my AP chemistry exam? And you will get every electron configuration question right. So I hope that helped alongside the topics I went over in the video, and I wish you a great day. Goodbye.